Hello everyone, in this video I'm going to give you a quick overview of a DC to DC switching regulator. If you are designing any electronic design and you are conscious about not losing the, the power in losses, in heat losses, like a linear regulator, your product will likely have one or more DC to DC switching regulator. So the in a linear regulator, the heat, there is an input voltage which is typically higher than the output voltage, and then in a linear regulator there is a heat drop between input and output, and but the switching regulator on the other hand, the efficiency is much higher, and it does by kind of turning this input voltage to a certain period of time high and keeping it low for the rest of the time. And the ratio of this high and low periods determine how much output voltage is appearing on here. That will become clear as we discuss this thing. So this is typically all these components are inside an IC, but it could also be designed using discrete components. And the most important components are these two: a FET and an inductor, and then we have a capacitor and a diode. So what we do here is we drive this FET using a pulse width modulator, and the on and off ratio could change. What happens is when this pulse width, when it's high, the transistor turns on, charging this inductor, and then as well as providing the current to our output circuit. And then when it's turned off, this whole circuit gets disconnected, and the inductor, it's the magnetic field collapse. As a result, there is a back EMF, and this point gets negative voltage. And because this gets negative voltage, this diode is reverse biased, and this provides a path for the current to flow. And when this is disconnected, this capacitor also, which has stored its charge, also starts supplying the current. So in between this inductor and this capacitor, they both start supplying current to our circuit. And this whole thing, they work in a closed loop. And then the way it works is that typically we put two resistors here, R1 and R2. So this makes a voltage divider. And the voltage on this resistor R2 will be, let me write it down here. The voltage at the resistor R2, let's call it a Vref. Then Vref is nothing but R2 divided by R1 plus R2 multiplied by V out. This is the output voltage here. Now we can rephrase this equation, and we will get V out is equal to Vref multiplied by R1 plus R2 divided by R2. Or we could write it in this way: V out is equal to Vref plus 1 plus R1 divided by R2. Now what happens is this Vref goes to an internal comparator circuit, and this comparator circuit compares this voltage with respect to an internal reference voltage Vref, and Vref is typically, let's say, 1.23 volt. For example, for LM2576 IC has it 1.23 voltage. So there are other chips that has this at higher or lower than 1.23 volt. So now what happens, if this V out goes lower, tries to go, let's say we want to set this volt to something like maybe 3.3 volt, and the input is, let's say, plus 5 volt. for some reason, whatsoever reason, for temperature or output getting loaded more, this voltage drops down a little bit. In a very small amount, it tries to get down. When it drops down, this comparator senses it, the difference between Vref and this reference voltage going in, and as a result, it tries to increase the pulse width by a small amount, depending upon how much is the gap between this Vref and the Vref that's from external feedback. Now, because of this increased pulse width, this effect is on for a longer duration. As a result, this output voltage, it tries to increase, and as this voltage tries to increase, this is now closer to this Vref voltage. This difference becomes smaller, so this increased pulse width gets smaller. So that's how this whole thing works in a loop. On the other hand, if this V out is greater than 3.3 volt, then this feedback comes to here, and this Vref is higher than this internal Vref voltage, and because of that, this comparator chip senses it, and it generates a pulse width which is smaller than this previous pulse width, and as a result, this V out starts decreasing. So this whole thing, it works in a loop, and that's how we get the DC-DC regulator working. So in theory, we could design it using discrete chip, but the reason they are inside a IC, because that chip does some more functions, and one of the functions, for example, is the thermal cutoff. They have a kind of a thermal sensor, kind of a diode, and that diode you can think of is, it could be AND gating this thing. So if something like a thermal diode here, and thermal diode senses it, it will shut it down to 0 and resume it when its temperature comes back to a normal. Another thing that this IC could be doing could be the delayed start. So the moment you turn it on, they could have a RC kind of delay circuit, and that will turn this FET on only when it passes some time, for example 10 or 20 milliseconds or maybe more. So that's a second function this could be provided. The third thing that chip could be doing is to monitor the current and cut it off if the current goes beyond a certain limit. For example, in a short circuit or anything like that. So typically that could be like a 3 ampere cutoff could be sensed by the internal circuitry and will turn the whole thing off. There could be other things, for example, in order to control the EMI or a stable loop gain, there could be some RC element that could be doing those specialized functions. So typically, DC-DC switching regulator, we use an IC, but these are the external components that we will be using. There are few things, if you are designing a DC regulator, you have to be a little careful, otherwise this whole thing could create an EMI and the noise problem. One of the most critical things is this small capacitor at the input of this input as this chip, and this is often ignored because you may think that we are only concerned about the output capacitor to reduce the, for example, ripple at the output. So you can ignore that this is what's the use of this capacitor. We may have a one big bulk capacitor, that's it. So what's the use of this small capacitor? So the reason for this is that this input voltage is switching. Also, you can think of this getting on and off, and is switching at a very high rate on this particular node. So it must have a return path, and that return path, depending upon the area of this loop, this forms a kind of an antenna. And if you place this capacitor in your layout at a very far place, then this loop gets bigger, and that bigger loop starts radiating, and then you have an EMI noise problem. In a similar fashion, on the output side, you should have a capacitor very close to it, because this whole loop could be radiating and you want to keep one capacitor very close to this coil so that this loop area could be minimized. This diode, for example, should be placed very close to this inductor to again minimize this loop area of radiation. There are this other consideration, for example, the calculation of this inductor and the calculation for this capacitor that you need to that's required, and that will depend upon the switching regulator itself. And this, in addition to all these things, you need to have bypass capacitor, the layout for the whole circuitry. For example, if this switching regulator is providing supply to your CPU, you need to take care of these things. Besides all these things, there's one more factor you need to consider, is the frequency of this PWM. It may be fixed, for example, in LM2576, or you may have an external resistor that could be set, that could set the switching frequency of this regulator. Now, the frequency of this switching regulator decides how big this inductor could be. If the switching frequency is very high, you will need a smaller inductor size, which is what we will prefer. But making it a higher frequency also creates the EMI problem, because now it's switching at a very high frequency. You need to manage that high frequency noise into it. But hopefully, if you can manage this noise and if you design it rightly, higher frequency is usually better. But if you think that you could mess up with this layout or something, not managing the return path on input as well as the output, a lower frequency could be better. So I touched up some of the area. This topology is for DC to DC regulator in a buck converter from high to low, but by changing the topology, you could also design a boost converter where the input will be less than the output voltage. You can generate like a 12 volt from a 5 volt input. So I will cover those topology in another video. I hope this gives you an idea of how to set the voltage of a switching regulator, and we will cover some more details and design principles in another video. Thanks for taking a look.